Welcome to CyberExplain channel. Today we are going to discuss secure your AI, cloud, containers and secrets for ML workloads vertical bar CyberExplain. Hey everyone, welcome back to the channel. Today, we are diving into a super hot and critical topic, AI security, especially in the cloud. You might think security is security, right? But securing AI and machine learning workloads throws some unique curveballs our way. We are talking about sensitive training data, complex model artifacts, specialized compute like GPUs, and intricate deployment patterns with containers and Kubernetes. It's like securing a high-tech laboratory with exotic chemicals, where a single misstep can have huge consequences. So, let's explore why traditional security needs a bit of a twist when it comes to AI. AI absolutely loves the cloud, and for good reason. The elasticity, the specialized services, and the sheer compute power are a perfect match for demanding ML workloads. Think about spinning up hundreds of GPUs for training a massive language model. That's something only the cloud can easily provide. But this deep integration means that cloud security becomes AI security, and vice versa. We need to be extra diligent because a breach in your AI pipeline could expose vast amounts of sensitive data or even lead to intellectual property theft of your precious models. It's a double-edged sword, immense power, but also immense responsibility. Let's kick things off with the absolute bedrock of cloud security, identity and access management, or IAM. For AI, this means making sure that only the right people and, crucially, the right automated services have access to your models, data, and compute resources. We are talking about applying the principle of least privilege rigorously. This isn't just about human users, it's about the roles your ML training jobs assume, the service accounts your Kubernetes pods use, or the managed identity assigned to your Azure ML workspace. Overpermissioning here is a massive vulnerability, making it easy for an attacker to move laterally if they compromise just one component. Next up, data security, absolutely vital for AI. Your training datasets often contain proprietary information, PII, or even sensitive medical records, and your trained models are valuable intellectual property. So, we need to ensure this data is encrypted both when it's just sitting there in storage, at rest, and when it's moving across networks, in transit. Cloud providers offer robust services for this, like AWS KMS, Azure Key Vault, or GCP Cloud KMS, which let you manage encryption keys. It's not enough to just store data, you must protect its confidentiality and integrity throughout its life cycle, from ingestion to inference. Cloud providers offer incredible managed AI services like AWS SageMaker, Azure Machine Learning, and GCP Vertex AI. While these services abstract away a lot of infrastructure complexity, *U* are still responsible for configuring them securely. This means properly setting up network access, ensuring service endpoints are private, and defining precise IAM roles for what the service can do and what data it can touch. Don't just accept default settings. Always review the security posture, scan container images used by these services, and audit their activity to catch anything suspicious. It's about shared responsibility, and your part is crucial. Let's get concrete. Imagine you are running an ML experiment in an AWS SageMaker notebook instance. This notebook needs to pull data from an S3 bucket and save model artifacts back to another. The secure way to do this is to assign an IAM role directly to the SageMaker notebook instance. This role should have only the permissions to read from the specific input S3 bucket and write to the specific output S3 bucket, nothing more. You wouldn't give it full S3 access, right? This prevents a compromised notebook from accessing unrelated buckets, significantly limiting blast radius. It's a classic example of applying least privilege to a managed service component. The biggest pitfall we see with cloud AI security, hands down, is overpermission service roles. It's so easy to just grab a power user role or give S3 full access to get things working quickly. But this is a ticking time bomb. An attacker compromising a single ML job or notebook instance that has broad permissions can then access, modify, or even exfiltrate vast amounts of data across your entire cloud environment. We've seen breaches like this, where a seemingly small compromise turns into a data nightmare because of overly permissive roles. Always scrutinize those permissions. Alright, let's talk containers. If you are building or deploying ML models, chances are you are using Docker containers. They package your code, libraries, and model dependencies neatly, ensuring your model runs consistently across different environments, from your laptop to a cloud Kubernetes cluster. This portability is fantastic for ML reproducibility and deployment. But containers also introduce new security considerations. What's inside that image? Where did it come from? What privileges does it run with? We need to make sure these portable units of execution aren't carrying any hidden vulnerabilities. The first line of defense for containerized ML models is securing your container images. Think of an image as a blueprint. If the blueprint has flaws, everything built from it will too. We need to focus on a few key things: building images from trusted base images, keeping them as lean as possible to reduce attack surface, scanning them regularly for known vulnerabilities, CVEs, and storing them in a secure, private container registry. Tools like AWS ECR, Azure Container Registry, or Google Container Registry, coupled with image scanning solutions, are non-negotiable here. A vulnerability in a base layer could compromise your entire ML pipeline. Now, where do all these amazing containers run? Often, it's Kubernetes, especially for complex, scalable ML training jobs or model serving. Kubernetes, or K8s, is an incredibly powerful orchestration platform. It can manage hundreds or thousands of ML training pods, ensuring they get the right compute, storage, and networking resources. But with great power comes great complexity, and thus, great security responsibility. Securing Kubernetes is a beast of its own, but absolutely vital for protecting your AI investments. Misconfigurations here are unfortunately common and can open wide doors for attackers. Let's dig into our core scenario, securing Kubernetes deployments for ML training jobs. When your ML training job runs as a K8s pod, it needs to access data, maybe pull secrets, and write logs. We secure this by using service accounts and role-based access control, RBAC. A service account is like an identity for your pod. You then link roles, which define permissions within the cluster, to that service account via role bindings. This ensures your ML training pod can only do things like read from specific config maps, write to certain PVCs, persistent volume claims, or access external cloud resources via an associated cloud IAM role. No broad cluster admin for your training jobs. Beyond who can do what, we also need to control what can talk to what within our Kubernetes cluster. This is where network policies come in. For an ML training job, you might want it to only talk to your data storage service, a metrics server, and perhaps egress to an external API for specific data. It certainly shouldn't be initiating connections to random internet IPs or other unrelated internal services. Network policies act like internal firewalls for your pods, defining rules for both ingress, inbound, and egress, outbound, traffic. This segmentation is crucial to prevent lateral movement if one of your ML pods gets compromised. What happens after our secure image is deployed and running as a pod? Runtime security for containers is all about monitoring and protecting that active environment. We are looking for anomalous behavior, a training job suddenly trying to execute into other pods, or a model serving container trying to access sensitive system files. Tools like Falco or open source solutions can monitor system calls and raise alerts. Also, applying security contexts in your K8s pod definitions, like running containers as non-root users and disallowing privilege escalation, is fundamental. It's about keeping a vigilant eye on what's happening inside the container, not just getting it started securely. Our Kubernetes scenario is great, but let's be honest, K8s configuration can be tricky and mistakes happen. One common pitfall is leaving the Kubernetes dashboard exposed to the internet, often with weak authentication, which is an attacker's dream. Another is running containers in privileged mode when they absolutely don't need to be, essentially giving them root access to the host. Think about the Equifax breach, where an unpatched vulnerability led to massive data loss. While not K8s, it highlights how a single overlooked configuration can become a major incident. Always validate your K8s manifests, run security scans on your cluster, and follow best practices for hardening. AI isn't just software, it runs on some pretty serious hardware, especially GPUs and TPUs, or tensor processing units. These are the workhorses for deep learning, crunching numbers at incredible speeds. While we're mostly in the cloud, understanding the underlying security of these specialized compute resources is crucial. They have their own firmware, drivers, and often run their own mini operating systems, creating unique security considerations. Securing them isn't just about cloud VMs, it's about the entire stack from the bare metal up. We need to think about how these powerful units are isolated, updated, and protected from misuse. In the cloud, you are usually sharing physical hardware with other tenants. So, how do cloud providers keep your super secret ML training on a GPU separate from someone else's? They use powerful virtualization and isolation technologies. This ensures that your GPU instance is logically separate and protected from other workloads running on the same physical machine. Technologies like hypervisors, secure enclaves, and specialized hardware extensions provide this crucial layer of isolation. For us, it means trusting the cloud provider's underlying security, but also making sure we configure our own virtual network, storage, and IAM boundaries correctly on top of that. Even though you might not directly manage the firmware on a cloud GPU, understanding its importance is key. Firmware vulnerabilities can be deep and hard to detect. Cloud providers are responsible for keeping these updated and secure. For any operating systems you do control on your compute instances, like a custom AMI for SageMaker or a VM for a K8s node, regular patching, hardening, and configuration management are non-negotiable. Don't forget, an ML training instance might run for weeks or months. Keeping its OS patched and secure is vital to prevent exploits from compromising your job or the underlying host. Think of network segmentation like building a medieval castle with moats and drawbridges around your most valuable assets. For AI systems, this means dividing your network into smaller, isolated segments, each with specific rules about what can enter or leave. Your ML training environment should be separated from your production model serving environment, your data ingestion pipeline from your development sandbox. If an attacker breaches one segment, they can't easily jump to another. This containment strategy is critical for AI, especially given the sensitive nature of the data and models involved. It's about limiting blast radius. In the cloud, your virtual private cloud, or VPC, is your own private, isolated network. Within that VPC, you'll create subnets, public subnets for things that need internet access, like a load balancer for a public-facing API, and private subnets for your sensitive ML training jobs, databases, and model repositories. Always deploy your core AI compute and data stores into private subnets with no direct internet access. This architectural choice is fundamental. It creates a strong first line of defense, making it much harder for external threats to reach your critical AI infrastructure directly. Once you have your VPCs and subnets, you enforce those network segmentation rules using firewalls and security groups. For example, An AWS security group attached to your ML training instance might only allow inbound traffic from your specific data ingress service on port 22 for SSH, but only from a jump box, and outbound traffic only to your S3 bucket. It blocks everything else. These are stateless and stateful packet filters that control ingress and egress at the instance or network interface level. Don't be too permissive here. A common mistake is allowing 0.0.0.0/0 to SSH or RDP, which is just inviting trouble. To really lock things down, especially for managed cloud AI services, we leverage private endpoints and service controls. Instead of your ML models talking to S3 or Azure blob storage over the public internet, even if encrypted, you can configure private endpoints. This means all communication happens entirely within the cloud provider's network, never touching the internet. GCP's VPC service controls take this even further, creating security perimeters around your data and services to prevent data exfiltration to unauthorized projects or locations. This provides an extra layer of defense, making data breaches significantly harder even if a service or identity is compromised. Why all this network segmentation? To prevent lateral movement. If an attacker gets into one part of your AI environment, say a staging ML model server, without strong segmentation, they can easily hop to your production data lake, then to your training cluster, and then potentially to your sensitive intellectual property. Network isolation acts as a series of barriers. Each segment requires a new, authenticated, and authorized connection. This significantly slows down attackers, gives your detection systems more chances to catch them, and dramatically reduces the potential damage of a breach. It's all about containment. Okay, let's talk about secrets. What kind of secrets does an AI system even have? Well, quite a lot. Think about API keys to external services, database credentials to pull training data, access tokens for internal microservices, or even sensitive model weights that need protection. Hardcoding these into your code or configuration files is a huge no-no. It's an easy way for an attacker to gain privileged access if they compromise your repository or a single container. We need a robust strategy to manage these sensitive pieces of information, so they are never exposed unnecessarily. The solution to the secret life of AI is centralized secrets management. Cloud providers offer excellent services for this: AWS Secrets Manager, Azure Key Vault, and GCP Secret Manager. These services store your secrets securely, encrypt them, and allow you to manage access using IAM policies, ensuring only authorized services and users can retrieve them. They also handle secret rotation automatically, which is a huge benefit. This means your ML training jobs or model serving applications never directly see the secret value, they just request it from the vault, and the vault handles the secure delivery. So, how do your ML training jobs or Kubernetes pods actually get those secrets from the vault securely? It's all about integration. In Kubernetes, you can use a secrets CSI driver to mount secrets from a cloud vault directly into your pods as files, or use environment variables. For AWS SageMaker, your notebook or training job's IAM role grants it permission to read from Secrets Manager. The key is that the secret itself is never part of your container image or code repository. It's retrieved dynamically at runtime, dramatically reducing the window of exposure and ensuring secrets are only available when and where they're needed. Let's bring this back to our K8s scenario. Imagine your ML training job needs a credential to access an external private dataset hosted on a third-party API. Instead of baking that API key into your Docker image, you store it securely in Azure Key Vault. Your Kubernetes deployment then uses the Azure Key Vault provider for Secrets Store CSI driver. This driver allows your pod to mount the secret from Key Vault directly into its file system. When your Python training script tries to read MNT Secrets API key, it gets the value securely fetched from Key Vault. This way, your secret is never directly in your K8s manifest or even visible in Kubectl describe pod output. The counterexample, and a very dangerous pitfall, is hard-coding secrets. We've all seen it: API keys directly in .py files, database passwords in plain text in dockercompose.yml, or access tokens committed to a Git repository. This is a massive attack surface. If that code or config ever becomes public, even accidentally, like a public GitHub repo, those secrets are instantly compromised. It's a recurring pattern in major breaches. Always, assume any secret not in a secure vault will eventually be exposed. Treat your secrets like the sensitive, volatile chemicals they are, and keep them locked up. We've covered a lot today. From securing your cloud AI services and IAM, to hardening your Kubernetes deployments for ML training, protecting specialized compute, segmenting your networks, and managing those crucial secrets. The key takeaway here is that AI security isn't a one-time setup, it's a continuous journey. Models evolve, infrastructure changes, and new threats emerge. So, keep learning, keep auditing, and keep applying those security best practices. Your innovative AI systems deserve the strongest protection you can give them. Remember, building secure AI systems means thinking about security at every layer, from the very first line of code to the underlying infrastructure. It's about designing for security from the ground up, not trying to bolt it on later. By applying the principles we discussed today, least privilege, defense in depth, robust access controls, and diligent monitoring, you can significantly reduce the risks associated with your AI deployments. Keep those questions coming in the comments, and don't forget to hit like and subscribe for more cybersecurity insights. Stay secure, build smart, and I'll catch you in the next one. Thanks for watching. Subscribe to the CyberExplain channel. See you on the next video.